Hello and welcome to HCI 509, Research Methods and Statistical Analysis. In this lecture, Lecture 13, we'll talk about regression. So let's get started. We just talked about correlation in the last lesson. So why bother with regression? Well, it helps to show the difference between correlation and regression to provide some context. Correlation only allows us to study two variables at a time. Regression analysis, however, allows us to investigate the relationship among one dependent variable and multiple independent variables. In HCI-related studies, regression analysis is really used for two main purposes. The first is model construction, and the second is prediction. Let's talk about model construction first. When we have model construction, the interest is identifying the quantitative relationship between one dependent variable and multiple independent variables. Really, we're trying to find a mathematical equation based on the independent variables that best explains the variances in our dependent variable. Prediction, on the other hand, is where we're trying to predict the value of a dependent variable based on a set of known factors. These known factors are also called predictor variables or independent variables, and the dependent variable is called the criterion variable. So prediction and model construction are closely related. We're trying to predict the values of the criterion factor, and we need a robust model to do that. Let me give you an example. Say you have a house and you're thinking about putting it up for sale. When you put it up for sale, you need to determine a price. That would be our dependent variable, the price that we will list our home for sale. Now, there's a number of independent variables that go into that prediction. These factors might be the number of bedrooms, the number of bathrooms, the square footage of the home, whether it has a basement or not, the age of the home, whether it has a swimming pool, the size of the lot. All of these will help you determine the price, but not all of them are equally important to determining the price. If we were to look at other home sales in the last 6 months or so in your area, you can get the amount of square footage, the lot size, the bedrooms, the number of bathrooms, whether it's got a swimming pool or not, and come up with a model that uses these independent variables or predictor variables to come up with a criterion variable or a dependent variable, which will be your price. So how do we go about calculating regression? Well, we have to choose a method, and there's two methods we'll talk about here. It all depends on our research objective. We have one called simultaneous regression, where we're finding the relationship between the dependent variable and the independent variables as a collective group. So we would take all the independent variables that we collected, and those would help us determine the price of the house that we want. So using the example of the house price, we would gather all these independent variables, square footage, lot size, whether it has a pool, whether it has a basement, number of bedrooms, number of bathrooms, age, and many others. And we would look at those as a group and use those to determine the price of the house that we want to put it up for sale. Another way is hierarchical regression. So we come up with a model that explains the relationship between the dependent variable and each individual independent variable. So instead of with simultaneous regression, we look at it as a collective group. With hierarchical regression, we look at it step by step. Let's talk about simultaneous regression. When we talk about regression, most people think of regression as simultaneous regression because it's the most widely used. Sometimes it's called simultaneous multiple regression too. So we take all of the independent variables and we enter them at the same time into our regression equation. And we'll find out the percentage of variances in the dependent variable that can be explained by the independent variable as a group. Remember that R squared that we talked about with correlation? That was an explanation of how much of the variance is explained. So if we have a significant R squared, it suggests that the independent variables as a group have a significant impact on our dependent variable. It's nice, but it's not really sufficient if we're interested in the impact of each individual independent variable. Let's go back to that house sales price example. We're trying to figure out the impact of each independent variable on the house price. So we can see what we should highlight in terms of supporting its value. For example, if square footage was what's important, maybe that's what we put in the marketing listing for our house. Hierarchical regression again. So the independent variables are entered one at a time into the regression equation. And the order of the independent variables matters. It's determined by a theoretical model. What do you mean by theoretical model? Well, there's two categories. We consider them to be important according to what we've seen in previous literature, or it could be by what we've observed on our own. And the variables that are not very interesting, but have an impact on the dependent variable, are considered covariates. Let's go through an example here. We have a user study that investigates target selection tasks using a standard mouse. So we have some targets on the screen, and we have a mouse, and we're trying to move the location of the mouse towards that target. So one important dependent variable would be the task completion time. And we want to know what affects that task completion time. What makes people perform that task better? So there's a number of different things that we could consider. The size of the target, how far they have to move the mouse, how much experience they have with computers, the age of the user, and so on. So we might have a data set like this. Notice it's ranked by the first column, or age. Then we have computer experience, the size of the target, the distance we have to move towards that target, and then our dependent variable is the time it takes to do the task. So to find the relationships among these factors, we conduct some kind of regression analysis using the task completion time as our dependent variable and others as our independent variables. So we would have, in this case, 4 independent variables and 1 dependent variable. The independent variables are age, computer experience, the target size, and the distance. And we would go off of what we know in the literature or our own observations to determine which of these we evaluate first in our model. Now with simultaneous regression, let's take a look at that same example. We want to find the relationship between the task completion time and all of those independent variables as a group. So here we have the same data set with the same 5 columns. And the results might look like the following. So we have model 1, that's how JASP refers to it. We have an R value of 0.858 and an R squared of 0.736. So that means that 73.6% of the variance in the task completion time is explained by those 4 independent variables. You can see this is producing quite a large F value of 41.147. We have 2 sets of degrees of freedom, 4 and 59, and you can see the significance is quite low, which means that we have a significant relationship between the task completion time and the 4 independent variables. And sometimes you might see R squared mentioned as adjusted R squared. Adjusted R squared just means that you have an additional reduction based on the independent variables you've added that don't really add to the variance explanation of the model. So in JASP, you would go up to regression, the regression tab, and then you'd enter in the dependent variable, and then you'd have several covariates, which are these three. Now, the example that's given here is one of the standard JASP examples on album sales. We can see here that it's really drag and drop, a nice tool for doing this type of simultaneous regression. With hierarchical regression, we need to look at each independent variable separately. So here we have these 5 columns. Remember, task time is our dependent variable. And we're trying to see how each of these others, age, computer experience, target size, and target distance, impact task time. So let's say that we've done some previous studies, maybe a pilot study, or maybe we've looked in the literature. We found that target size and navigation distance are the most important factors to examine. And again, this is determined in advance. Sometimes you'll hear about stepwise regression, which is similar to hierarchical regression, except instead of our own knowledge or previous research telling us which are the most important factors, we allow the computer, or in this case, the software tool, to determine those. A lot of times this is going to give us misleading information because we, as researchers, by telling it which of the independent variables we want to evaluate and in which order, we are providing some context that the software tool really can't do. So a lot of experts, when they talk about stepwise regression versus hierarchical regression, many of them say use hierarchical whenever possible, and stepwise is where you kind of just throw it at the machine. In many cases, it won't get it right because the subject matter expertise that you have is not going to be matched by the computer. So let's say we find that target size is the first block of independent variables, and navigation distance, then age, then computer experience will be in the subsequent blocks. We construct these as different models. The first model will be target size, then 2 will be navigation distance, 3 will be age, and 4 will be computer experience. Now notice what we have here is we have 4 different models, but we have an additional column here called R-squared change. And what R-squared change means, it's the difference that adding that particular model, that additional independent variable, does to our R-squared. So we start with 0, and the first model is going to explain 31.9% of our model. The second one brings us up to our R-squared of 40.3, but that adds only 8.4% to our model. So the first model does task completion time and target size being the first independent variable, which we may have obtained for our own studies or observations, that is the most important determinant. So we can see by looking over at the significance in the far right column that it's a significant percentage of variance, meaning it does have an impact on that task completion time. It explains 31.9% of the variance. And you can see here how we would report it. F1, 62 equals 29.054, which we get from the F column, and the p-value is really, really small. We're very confident this has an impact. Now, if we go to the second model, now the R-squared change represents the additional variance. So we can see here, as I explained earlier, that model 2, by adding navigation distance, explains another 8.4% of the variance. It's still significant. It just doesn't explain as much of the variance in the model. So what we would say is that navigation distance also has a significant impact on the completion time. And you can see here we have one less degree of freedom on our second model, but it's still significant. And we could go on with the third model and find it significant in the fourth one as well. Notice that the R-squared change is not in order. You can see that the second model added 8.4%, the third model added 18%, and the fourth model added another 14%. If we were going to add those up, we can get to that 73.6%. One thing to note, the adjusted R-squared, which we don't see here, would penalize the model if we add independent variables to our model that don't help explain the variance. These four all do contribute, but it's possible to have a number of independent variables, some of which have no impact, and that will negatively affect our R-squared, and that's called the adjusted R-squared. So in JASP, doing the hierarchical regression is not as straightforward as the simultaneous. So we enter a linear regression, but we only start with the most important independent. So for example, this is using that album play example in the JASP examples. And you can see here we start with adverts only. And then when we get the model done, there's another space where we would add an additional aspect. Let me go to JASP now. So here we have the example that we were looking at in JASP. And you can see here, this was our simultaneous model. We had the other three covariates to determine our dependent variable sales. But now if I would do a hierarchical model, see how it has add to null model here and it has a check mark? I would first run the model, and the add to null model would give us some results. Then if I check another one and I run it, I'm going to get additional sets of results. The third time I'm going to add it and I'm going to get another set of results. So this add to null model takes the previous baseline model and helps us determine that adjusted R-squared. Now it's not intuitive inside of JASP. In other tools it is. I've provided an additional link to how to do hierarchical models in JASP in the Blackboard. So you can see here that the second step has us entering a new linear regression with more variables, one at a time, until we build out our model. So it's an iterative process. It's not a single process like the simultaneous. So with the second one, we click on the tab Model down here, and then we select the independent variables from the previous entry as the null model. So as we build them, we just keep clicking, like the example I showed. Now to summarize, correlations find the relationships between two variables at a time, but regressions allow us to establish relationships between one dependent variable and multiple independent variables. Now remember, there's two kinds of regression we talked about here. Simultaneous regression finds the relationship between the dependent variable and the independent variables as a group, and the hierarchical regression explains the relationship between the dependent variable and each individual independent variable. So thank you. I hope this has been very informative, and I'll see you next time.